Okay, so this week we're gonna get into chapter 6. And of course, we're still in Newtonian mechanics for rigid bodies, kinetics, and we will get into the rigid body motion. Of course, in rigid body motion, the very first one you need to know is called the GPM. It's your general planar motion. And there are two types that you have to know. And of course, here is a little diagram to make you visualize how this motion is going on. So we call the very first one the force imbalance is your translation, and the other one is your moment imbalance, and that's your rotation. So you got to understand we have so many structures in this world, yeah, in this on this earth, and they're all in balance, meaning they are structured or built pretty much in balance. All the forces are, because if the forces are not in balance, they're not going to be standing where you put them to be. Okay, from buildings, also of course every product that we build, every product that we manufacture, even if it is a small product that you put on a table, we still need the forces on that product or object to be in balance. Okay, meaning like we don't want the external forces acting on it, because every time you have an external force, it is going to make that structure or the object or the rigid body gonna go into some sort of motion. Okay, so you need to stabilize the structure objects so you will not have any kind of motion of these balance structure or balance objects. So every time you have a motion, it means that you have some sort of problem, okay, in your stability. So if you have your force imbalance, you are going to get this type of motion, and that's called translation. And if your moment is messed up, right, and your moment is not in the way we set it up to be stable, but the moment has some imbalance, then you're going to get another type of motion, and we call that rotation. So when your moment got problem or issue, your object is going to go into rotation. Yeah? So we have to make sure that we got this moment correctly in the object or any structure that we attempt to stabilize. So now you kind of get what is static and then what is dynamic. Static is everything that is in stability, and dynamic is we destroy something, is destroying that stability. If that was the force, you're gonna get destruction of that static, okay, position, and you will go into your object or body is going to go into a type of motion, and we call that translation. If we try to destroy the stability of the moment in your rigid body or object, then you will get moment imbalance, and at that time your object or your structure is going to go into rotation. Okay, so make sure that you get this translation and rotation, two different motion, two different types of motion, and we call these two combined general planar motion. Okay, so you have translation, so go and translate from here to that position, and at the same time your moment is not in stability, so it will also rotate. So when an object is translating and rotating at the same time, we call that type of motion general planar motion. Okay, and you need to get this one because there are so many things in the world that is in this type of motion. Your GPM. All right, your background knowledge. We have already studied Newton's equations, many of them, especially 1, 2, and 3, and of course the associated aspects of these motion. Okay, so you have your rigid body Newtonian mechanics. You need to know the center of gravity. Of course, this W is your weight, and of course it's applied at G is your center of gravity. Try to notice that we've been calling gravity in terms of acceleration, in terms of center, in terms of force. Okay, so this is a third one that you're seeing. We're calling it the center of gravity. We have acceleration due to gravity, and then you have gravity itself, which is a force. And then we have moments. Moments are forces in causing moment, and I'm going to teach you what moments are. Okay, it's pretty easy because you're just trying to find where's a point in an object that is going to cause that object into some sort of imbalance. Okay, all right, mass moment of inertia is your resistance. Every time you say inertia, meaning like your object is resisting to something. So in this case, your rigid body is resisting to angular acceleration, because again, acceleration is one of the aspects of a body that is in motion. So every time a body is in motion, since the body is composed of mass, and the mass is composed of so many little tiny particles, and they all are in motion at the same time. Okay, so anyways, as long as you have a body or a mass, it has moment already in there. Okay, why? Because I'm gonna go into this deeper knowledge in future slides, but right now just understand that every time you're dealing with mass, you're dealing with a resistance. It doesn't want to move. Okay, your mass want to stay where it is because it's been subjected to this guy, gravity, and the mass itself, by the way, because the mass they are bonded together. Not permanent bond. There's no bond that is permanent in any of the structures. You always have some space in between any two particles, even if these particles are very, very small. All right. So if you really think about it, and this is one reason why every object, in any product that you manufacture, they have a specific life cycle. Human has a life cycle too, right? And then of course that life cycle always cycle means it begins somewhere and then it ends somewhere. And you begins when you are born, 0 year, and then you die whenever you die. So 60 years, 70 years, 80, so and so. Of course, nobody really lived up to 140 or 150 years. So what I want to say is, like, if we really go back to the mass always have a resistance to any type of motion, because mass itself is in bonds. All right, in bonds, some sort of bonds. We have many different kinds of bonds between physics level of the particle. You gotta understand that your system has too many levels. Okay, they're in quantum, and then plasma, and then atoms, and then molecules, and then get bigger and bigger, and then you. Yes, of course, we're just always giving example with the human body, especially composed of the carbon, hydrogen, and oxygen. Of course, if you think about it, just a regular lifeless rigid bodies or particles, then they have their own chemical structure. So chemical structures, they are in a second level. Okay, so the very first, your base level is always at the physis, very tiny little things, and then you have some chemical structures, and then of course your bio, and all the non-living things, they stop at the chemical structures. Again, we go back to why mass has an inertia is because of these bonds between them. And we have already studied in physics, every time you have two objects or two bodies or two particles, they have a tendency to attract to each other. So they have a forces on subjecting to each other. So we call it attractive force. So one body always attract the other body. Sometimes they repel. Depends on the material too. And these bonds are making that inertia. Okay. So of course we also have external forces. Because if you study, then you come to understand we have nothing but the little tiny particles and very, very big particles. And little tiny particles are in system of some sort, living or non-living system. Of course, our reference is always this planet, which is the planet Earth. And then you have this giant, rigid body, which is your Earth, composed of so many things on it, and one of them is you. And of course, all of that create incredible amount of gravity and forces in between them. And that create inertia for every mass, by the way. So when you are in scholarship, you gotta use your brain, because you're a student. When we say student, is someone who study something. Okay, if you don't study, then you're not a student. And sometimes I don't know why you're even at school doing what. I have no idea. Maybe you just want to get a degree to promote it or something. I don't know. But you don't need to come to university if you don't want to study something. Okay, and it's more than getting a job. It's really, really more than getting a job. Because even though we have this planet, and we have this body, and we're living, we have no idea why we are first door. Okay, and everything that we're studying, it just sometimes at one point you're gonna feel that. Okay, it's in our body, it's in our genes. Go to the very smallest level. Your knowledge is not only at the human level. So anyway, so studying it, we're trying to understand to the smallest thing that we can get to, with the available technology. And we found that every time you have a mass, there's some kind of a mass moment of inertia. And that thing is practically resisting to motion or aspect of motion. So here we identify the mass moment of inertia resistance to the angular acceleration. All right. Of course, then we're going to put that into a mathematical formula. So you always have this sigma just telling you sum it up. And then of course the MP is your mass moment, and then of course we're going to have all of this. Okay. Here is your G. Right now, of course, you don't understand. I'm going to go into each one of them, and then I wouldn't say, this is just a big thing which includes all of this. So you have your force here, MA, and then you have your radius here, which is contributed by your center of gravity, okay? And then of course you also have like a mass moment of inertia, and then your angular acceleration, and everything is contributing, okay? If you sum it up, it's going to contribute to your moments. Of course you want to know like what is this little thing here, why we have P here. That's just the symbol for a point, because we go by point. It becomes point because when your mass is so small, so from your system level you're looking at these little tiny things. At that time we start to just take it as a point to make it easier for the calculation. Alright, so that's just a sum again because of this symbol sigma, the sum of moments, m for the moments, about a point, and this p is your point p. Of course, it's gonna give you the total torque, or another common word for moment is your torque, So torque acting on a rigid body. Let's just imagine there's a rigid body here representing these moments. And that torque, every time we think about torque or moment, we calculate, then we always go about a point, with respect to a fixed point. And of course, this is your moment of inertia, which is this guy here, of the body about that point P with its C, the angular acceleration. And that just showing you every time you think about the moment, again, is a rotation, is this motion. So the moment can cause the rotation if that moment or the point, this point is very important, is not in a location, okay, that is going to stabilize that rigid body. So as soon as your moment fixed point is not, okay, or the point where your gravity is subjected to is not at a balance point, you're gonna get some sort of rotation. All right. Of course, and when you take a look at this, you know that that's just a vector, because this is dark here. Your R is, so just showing you the position vector from a point to the center, center of mass or center of gravity. So there is also a distance, a very, very important distance, and we call that the position vector from that point P to the center of mass, or G, okay? And that R, and then times, of course, your force, which is your mass, and your acceleration, regular acceleration, not angular, okay? So regular acceleration at the fixed point. So you've got to understand, we're going back to torque, okay? And the torque of this side is due to your linear acceleration, because you're seeing the regular acceleration, so therefore we call it linear acceleration, and the other one is your angular, which will cause that rotation. So you have a translation, this side is a translational motion, and of course that side is a rotational motion, and you have your general planar motion contributing to the total torque about that point P. All right, so that's how you need to understand when you see the equation. Okay, of course your course is not gonna stress on your calculation, even though some student requested me to give you the calculation, which I am doing that for you. Okay, all right, and then we will get into another section, and that's center of mass and gravity. I have already explained what is the center of gravity, what is the center of mass. Of course, you need to know if they're the same or if they are different. So when you take a look at it, the very first one is your center of gravity, and that's a balancing point. Okay, always remember your static and your dynamic. Okay, so let me get my pen. So anyway, a balancing point, it means that the mean location, mean average, average location of that gravitational force. Every time you have a gravitational force, that force is going to be acting on the body of the body of interest. Okay, and we are looking at the G point. Yeah, so the mean location of gravitational force, and that gravitational force is very important because it's going to create a balance. Yeah, and we call that the balance point, because if you disturb that balance, you're going to get some motion. Yeah, so right now look at that, we cross the fork and the spoon, and now we're setting that right here. Look at this with this little a coin. See, so no, this is not spoon, actually this is a fork, and fork, and we put the coin in between and set that on this, okay, glass, okay, glass mug. And what you're witnessing right here is how they are in, okay, some sort of balancing point. Okay, so right here, so you're trying to find where is the center of gravity, and we set the four objects at that point. Yeah, and it stays. Okay, of course you've got to try to differentiate why. Yeah, so these two forks and a coin are standing on a glass. Okay, I'm just trying to show you a real world world example. Okay, it's just a small demonstration showing you where the center of gravity is. If you have time, you can try to find that point. Of course, in the lab a long time ago we did this. Okay, right now we can try, but it is going to be really hard for you. But I will bring, okay, these materials at one point in April, and you can try to find that point center of gravity, and you're gonna see how difficult it is to be able to get that balance. Okay, it will definitely come off, by the way, but I will torture you a little bit and make you find the point. Probably let's do one lap on it. So here you understand that when I say the objects or structures, or the rigid body, and of course we have 4 components in this system. So, and all the components in the system is in stable, okay, stable state, and we call that the structure is, or the system is stable. Yeah, meaning we do not have external forces destroying that stability in this system, because your forks extend outward and downward, and it of course distributes the weight and shifting the center of gravity into a position where it can balance. Okay, when you look at this 2 different example here, you can see it is they're standing on the very edge. Okay, see how the weight is on this side. Because the center of gravity is not only one. Yeah, this spoon has its own center of gravity, and that, not spoon, I mean fork, has its own center of gravity, and this another fork object has its own, and then the coin has its own, yeah, center of gravity, and of course this also has a center of gravity. Yeah, even though there is only 2 sentences here, you got to understand that we are looking at the mean location, meaning the average location of the gravitational force acting on a body. Okay, so be very careful. I totally underlined that for you. Yeah, and reading it will, you won't understand. You can read the English, and you can understand what it means written in English, but sometimes you don't really get what you read it. Okay, it's this word mean is average. Every time you see average, you understand that you're dealing with, even though it said it is a body, you are dealing with the average of the center of gravity. Okay, so the average of the location of the gravitational force. So here in this case, you have 1, 2, 3, and 4 of them. So you're looking at the combined center of gravity, of course, divided by the component number, is in line with the point, okay, of contact on that glass. And in other words, formal word is stable equilibrium. We're creating in this system a very stable equilibrium, which is going to keep everything in this position. Okay, it's just a clever way to show that an object doesn't have to be systematic or sit flat to the balance. Okay, it just needs its center of gravity to be supported. All right, okay. Of course, we go back to the definitions, and you must know these definitions. So the very first one is your center of gravity. You don't have to write it if you don't remember like this, but at least you should be able to write in your own words, what center of gravity means. So that's just a mean location. This is very important word, average, location of the gravitational force acting on the body. The center of mass, again, your mean location of all the mass in a given body. In a uniform gravitational field, they are located in the same place. Okay, why? Because it's a uniform gravitational field. A field, we usually use this word to describe, where this gravitational force is acting, on the body. So it's a uniform gravitational field. They are located in the same place. Make sure that you get center of gravity and center of mass. They are not the same. What is the difference? Gravity is force, and your mass is mass. Okay, and of course we are making sure that we know we're dealing with the average. All right, center of gravity. Why do we need to know where the center of gravity is located? It's very important. You really need to know where the center of gravity is in mechanical engineering technology. Okay, why? Because we build things. All right, now, so when drawing a force, okay, this is just your force diagram, So when you draw the force diagram, we usually use, remember, the weight of the object or body, and we write it like mass times acceleration due to gravity. So we call it mg, right? So that's this is where your force is placed, and this is where your gravity, okay, is acting on that body. So every time you need to know where the center of gravity is, look for, if a diagram is given to you, look for where is my mg point, and you're going to see it in the force, force diagram. If you are the person who is drawing the force diagram, then you have to think where to place it. Okay, depends on the given situations. Okay, centroid, center of gravity. When you deal with the center of the volume, and we call that centroid. And then of course you also have your center of gravity. You wonder, like, are they in the same location? Yeah. So if your object or a body has a uniform density, another one coming in, so your physics review, your centroid is equal to the center of gravity. If your object is a composite, okay, with non-uniform density, your density is messed up. At that time, your centroid, that's your center of the volume, and the center of the gravity, they're not the same. Okay, so the only time the center of the volume and the center of gravity they are the same is same mean as in location. Okay, don't forget it, we're dealing with the position of location. So that point is the same if your object has a uniform density. So now you got to know what rho is. Yes, what is density? I forgot. If you forget what density or rho is, it just we're looking at, because of this volume, you're looking at again your particles, your mass over that volume. Okay, so volume is more than a surface because you have in 3 dimensions. Yeah, and of course, let's say like you have volume. Yeah, and this object that I just drew here on this slide, and their mass in that volume. Okay, and when we look at the how dense the mass is in that volume, then we say mass over volume, and we call that rho, which is your density. And if you have these particles in uniform density in the object, your centroid, the center of the volume and the center of the gravity, is the same. Okay, so meaning like your mg, let's just make up a point, let's say it's right here. Yeah, so your mg point is going to be here, the center of volume is also going to be at this location, because your rho, or the density, which is mass over volume meaning like we are looking at the mass, okay, over volume. Yeah, in this volume, how much mass we've got. So that's how we're looking at it mathematically. Yeah, so every time you read an equation, you know that every time you deal with a ratio or a division, we're looking something against something. Yeah, and if your object is just a composite, meaning like it doesn't have a uniform density, it's just going like concentrating like whatever way it is, when you didn't blend it with a uniform force, then of course the particles inside of the object is going to settle in a different density pockets. Yeah, so if you have like a different density pockets, meaning like dense here, and then it's not dense and scatterly, poorly distributed here, and then you have all of this and so dense at that corner. So this is called composite, and it isn't uniform. Your mass is not distributed uniformly. At that time, the center of the volume is not equal to the center of your gravity. Okay, all right, and then let's go into the center of mass for a system of particles. Again, your particles, these are the components of that system. Yeah, so in your brain, every time you read, oh, I've got a system of particles, and then I am going to find the center of mass for that, and we understand the density, we understand the system, we understand the components of that system, your particles, and our strategy is to find the center of mass. Okay, where is the center? Okay, so now we draw it on a graph. So now we are going to make it really big, and so I am going down to 4 particles, particle 1, 2, and then 3, and of course 4, and then I'm going to start measuring from a reference, datum point right here, reference point right here at the origin. So from here to there R1, meaning my distance, meaning like the location of the particle is away from that reference point R1. Second particle location is away from this origin, your reference point R2 distance. And then your third point is away from that origin R3 distance. Your fourth particle is away from that system origin. And this, of course, x, y axis, because we're concentrating on this four particles. So particle number 4 is R4 distance away from that reference point. Yeah. So we gotta have a common reference point for us to be able to measure and compare how far away they are from the origin. Yeah. And of course our mean location, yes, and so this one has its own center of gravity, that one has its own, this one also has its own, and that one also has its own. So when you take a look at this four particle, where is the center of mass? It's got to be something that is the mean, okay, of all that mass, and that is going to be right here. After calculation, of course, how do we calculate it? We use this, okay. So mass times location. Of course, we're dealing with the center of mass and gravity here in this case. Sum of your mass, we have 4 of them. I is the number how many mass you've got. The mass are in terms of particle or bodies, yeah. And then of course, and then you have your distance, associate distance. Oh, you should say like the corresponding distance for these masses. And we will do algebra by putting this thing on that side. So when you put this on this side, it goes to here, yeah? So that divided by this, so we're looking at the sum of the mass times distance over mass, okay? Over the sum, over the mass, average mass. And you're going to get this distance, okay? So every time you want to find where the center of mass, okay, is going to be, you got to find the distance from your reference point, which is here, origin 0, 0, yeah. When you want to find that, all you have to just add your mass time r, okay, and divide it by the mass, right? This is a total, and this one and each one of them, okay? I come back here to tell you, based on my experience, I remember some students, they have issue with the symbol, okay? Also, there are many textbooks, they loosely use G. All right, and there's a confusion between the center of gravity and center of mass because of this, the usage of the symbol G, okay? Let's just go with, you can call this whatever you want to call, okay? But we use it G in many textbooks, and sometimes you will even see something like this, okay? In some textbook, that just symbol, okay? We can make any kind of symbol to represent any variable, okay? So do not confuse. Even if we use G, don't go with that's the center of gravity. No, in this example, symbol G is used to identify center of mass. Yeah, so I am trained to ignore it and not to use a symbol with one meaning, okay? Don't just use G is for gravity forever. No, G can be mass, G can be volume, and G can be anything that you want it to be, okay? Be very careful with that. I don't know why some of the professor also like to trick you to test you your knowledge or your understanding of the symbols. Okay, so trained your brain not to take it G for gravity, no, G for gram, like that. No, don't do that. Okay, just go with situation to situation. In this situation, your G represents center of mass. All right. Then, of course, we will get into the center of mass for a rigid body, and we will get into more points. Yeah. So we've got 1, 2, 3. Now we have another one. Of course, so this is actually RG. Yeah. See, now we use. Look at this. See like how we use a different symbol for this thing. And then of course we have another in here. So altogether we have IDM, meaning like there's so many like mass in there in this object or body. Okay, I mean there are many of them. And then of course we use the same equation, which is the sum of all the way go from 0 to the I particle or mass, and then times the distance, corresponding distance, so Ri, and then divided by the total mass. Okay, so every time you look at it, you know that you're dealing with a system of particles. Yeah, so when we say a system of particles, I always give you the human example right there. Of course, we have living things and non-living, stuff. And non-living stuff, we just draw like that. Yeah, it means everything in your house. Yeah, everything in the world, and of course, everything in the world, everything of the living thing or non-living thing, they are composed of some sort of particles. All the way to the smallest level. So anyways, a system of particles. Okay, and we calculate. Of course, you can also break it into, I just want to analyze this part or that part. I just want to analyze here or here, or here. So anyways, a system of particles can be able to put into many different kinds of levels and corresponding sizes. Okay, of course, a rigid body, we come to another one. In rigid body is a different equation that we use. Yeah, so look at this. So more getting into profile stage. So every time we deal with a profile, it's not easy like a very few particle system anymore. Yeah, it's more of a calculus kind of area that you're getting into. So that's why you start to see this wiggly integration sign right there. Yeah, mean like we are now getting into more complicated system. Yeah, which is a rigid body. So therefore, the entire equation to get this, of course, the distance of this average mass or the center of mass, it changes. Okay, it changes. So it's 1 divided by m total mass integration, and then we will integrate the locations, which is your r. And then, of course, we are going to do dm because of this integration mathematic operation. We always write this way. Yeah, every time we want to integrate the position, we write, integrate the position, according to the mass. Okay. Let me go back. I really want you to get it. Yeah, we integrate the position, and I speak it this way, according to the mass. Yeah, why? Because the distance and the mass, they always see like how they coordinate each other. So the point is that distance away from this origin. Of course, your reference, so where did you measure from, is very, very important. Yeah, so that's what this pair is about. Yeah, because your R is depending on the mass. Yeah, and your mass is again located at that. Yeah, and we will integrate it, divided by m will give you the rigid body, okay, average distance to that center of mass point. And then we will get into moments. And we will, of course, you need to know how to calculate it, but you don't have to do everything. Okay, only the equation that I'll give it to you in the PDF in your question and answer module in your Brightspace. So make sure you take a look at it and just don't, without looking at anything and just studying. Yeah, you must listen to my lecture, and also read the announcement, and then dig into the modules, and then you'll be okay. Yes. If you don't do one of them, I don't know. Okay. All right. So moment review. So you have rigid bodies. Every time we analyze rigid bodies, they have size of some sort. Yeah. So here is our rigid body, and it's a car, and it is composed of some parts in there. And then of course this is a free body diagram. So your force diagram is going to show you, see all the forces acting on that. So your mg, okay, here is a little point, and we have already studied, every time we see the mg, we know that that's the center of gravity point. So your forces apply at locations other than the center of gravity, they create a moment. Why? Because they disturb the stability of that, okay, rigid body. So now we look for the forces, and of course this is a very, very simplified version of the forces. In reality, you don't have just 1, 2, 3, 4. Okay, we simplify that. Just like we were arguing right last, just like this height, right, from the in order for you to understand this acceleration, or even say like, oh, like start from the ground and don't do it from the table to measure the point. Of course, this is, if you learn this from physics, you're going to say, oh, it's arbitrary and you can do whatever you want. But no, there is an absolute temperature, all right? And of course, the more accurate is actually to actually get it from the core, starting point here, by the way, your reference point. So you can also do it. This is really good for everything on the earth, okay? If you take it from the surface of the earth or ground, okay? Even the ground is, you have some height, okay, altitude according to, well, whatever. So if you start from the very source here to there is the best. Well, whatever that is, you can either use this or this or this in calculation. But then if we seek for the precision, then we need to carefully choose, all right, the best point. And so anyway, to get the height to position that, where is this mass? So anyway, so let's go back to here. And why do we do it is because the planet is so big, so therefore this little distance, of course, you can ignore it, However, if you want your rocket to come back to the spot, so you can be able to save the material instead of crashing into the ocean, a vast ocean, to come back to a specific point, then yeah, you really need to deal with this project and height. Yeah. Okay. So anyway, so let's go back to here. In rigid bodies, they always have size because they have mass, so therefore they've got the size and the shape. Of course, your forces applied at locations other than the center of gravity, they're gonna create the moment. Yeah. So how external force can like a tilt or a tip, all right, this a rigid body, okay, into some sort of rotation, okay, because you're going translation linear motion right here, and of course you have your gravity, gravitation force right there, and here is your center of gravity right there, and then you also have the normal force, on the wheel. Of course, in this situation, we are pointing to the wheel, so it's acting right here. And then, of course, your friction, because you have to overcome this in order for this thing to move forward. All right. So anyway, we have hit the major locations of the, and these are all average, by the way. Yeah, you can't just say that there are only two. No, in reality, you've got a gazillion of them here. Yeah. Okay. Anyway, then we'll get back to here and we will concentrate the moment. Yeah. So when you take a look at this, the moment is again your mass and then your R, okay? And we call it common word is torque, okay? So right now we are going to put, okay, instead of the mass, we will put the force, which is ma, okay? Acceleration is in there because you're in a motion. So the moment created by a force about an arbitrary, again, this is actually not a very good thing for the student to understand, because we do incredible amount of arbitrary. This is makes sometimes difficult for you to be able to understand the real thing. So anyway, so the moment created by a force about an arbitrary point P, okay, so here is the arbitrary point P, and it's been created by swinging this thing with your hand, okay? So here there's a point, and then of course that point is has gravity is going this way, okay? And then of course you are exerting a force in this direction. So these are all factors for you, yeah. And when you calculate, okay, this force where it acting on this hand, and from this point to the center, okay, of this little nut right here, and that's R, okay? So you will have a moment going anti, okay, clockwise rotation, okay, that way, and that's because of this, all right, force, which is this guy, is acting on this object about the distance, okay? So the force and the distance is going to create a moment, and the moment go that way, all right? It is hard for you to see. So outside you would see that your hand is, okay, trying to rotate. So I wouldn't say this is a nut. It looks like the head of a bolt or something. Yeah. So you are making this type of motion. So either you're taking it out or loosening it, or okay, tightening up, one or the other, because we don't know tightening is a counterclockwise or the clockwise. It didn't say, yeah. So we would just say like we're rotating this an object, okay, with a hacksaw head right here. It could be a screw, it could be a bolt or a nut or something, okay. And of course we turn it, rotate it in this way. So how did that moment happen? Because of the applied force and because of the distance, okay, from that force to the center, okay, of that object, or the little red one in there, and we get a rotational force, right, which is this guy, and we call that the moment. All right. So I just said, what is a moment? Moment is the force, all right, and the force is now bigger because we time it with this distance, okay. So every time you look at it, that's what you see. Moment is a force, but this force is now transduced into a bigger force, okay. Why? Because of this distance that we apply, yeah. So the longer the distance, the more force you've got, yeah. So over how this thing will get longer and longer, you got a bigger force at that point of interest, okay. See how powerful these mechanical equations are, yeah. So you can play with it. So you apply a little force, but you know that if you make it longer, you got a bigger force at the point whatever you want to apply. Okay, all right. So now let's go to the next one. So does a moment have direction? So now you gotta think about the moment calculation review here, and we know that, yeah, we just said it, a moment is a force, right? Because based on mathematical of course, equation, and you've got to understand where is this right moment direction is going. And it's going with this, see this a little red arrow there, I call it anti-clockwise, of course, because it's showing the way to describe that direction. Okay. So how do we indicate the direction? So how are we gonna show that? So first we're gonna put it, of course, into the unit vector. Yeah. So sometimes we have to use a vector for us to be able to describe the direction. Yeah. So unit vector, unit direction vector is what we're gonna use. Okay, to describe that. So we call this anti-clockwise direction. Yeah, in this case, because sometimes you're gonna have a many different way of using, okay, the directional vector, like up and down, if that's linear, right and left, or positive and negative. Okay. And of course, for moment, it is always mostly the rotational motion, so therefore we use it counterclockwise or clockwise. Okay. Then we will go into perpendicular moment arm method. So here again, you don't go into calculation, okay? Just listen, and there are only, I think, two equation, very simple equation for you to calculate for this course, because you are in a two-year school. So we will just do the level 1 for you. Yeah. Of course, you can use the knowledge to study the level 2 and 3 in dynamics. Of course, moment calculation, as always, we will put it into XY coordinates, okay? And here you can see the forces going in that direction, and our distance is here. You need this and this in order for you to be able to calculate your moment, okay? And here, this is just showing you your R is perpendicular to that line, okay? So from this point of origin, you go that way, and that's 90 degree along the path of this force, okay? So you can see R perpendicular, okay? And your F perpendicular is the other one. Yeah? So you have origin, your distance, and your particle is here, and the force is going in that direction. And you're going to branch out a perpendicular force downward from that point, and then of course close your triangle here, and you will get another 90 degree, and we call this component of that force F perpendicular. Okay, and you can be able to calculate F multiplied by this guy, or F perpendicular multiplied with this guy. Okay, and you will end up getting your moment about that point. Okay. Our force component method. I will not ask you this. Okay, you only need to know that. A force component method. Moment calculation, we will get into another one, xy, yeah, coordinates here. So xy coordinate has the origin here, and then of course you go rx, and then ry, you go from here all the way to your point of interest right there, the central, yeah, masses, and that's r, of course the force subjected to that. You're gonna need this and this to get the moment. In this case, we can break it down, right? Break these parent location and parent force into x and y components of these force, and x and y components of this position. Yeah. So we have this ry and then rx, fx and then fy. we're going to put it into a new equation to get the same moment, and that's your Rx times, yeah, Fy. So this Rx, you're going to time it with this guy, yeah, why? Because they are connected, yeah, on this path. And then you're going to multiply Ry with Fx, because if you trace the path, they are connected, okay? But you can translate this thing to that side. So see how the vectors start point, end point, start point, end point, and you could get that, which is the same as this guy translated, because they are making a geometry which is a parallelogram, yeah? So everything, of course, in engineering, our eyes are trained to see the triangle, square, rectangle, circle, yeah, and profile. So make sure that, like matrix, okay, you're gonna break down everything in your mind. Studying scholarship is you're working your brain and your mind to be able to, when you look at it, you recognize. When you recognize, you know what you're looking at, okay? If you don't recognize what you're looking at, there's no business studying, yeah? So train yourself to be able to understand what you're doing by looking at what you're looking at, okay? Even though it's on equation. So anyway, so let's go back. And this one, I will teach you how to do the cross product method. Because it's a type of mathematical operation like your differentiation or integration, and I already told you how to use this MATLAB, okay? Of course, you gotta use your AI because you didn't do calculus, okay? So therefore, you just have to do a shortcut to get to where we want to go. So anyway, so another operation is a cross product method, and of course, our goal is to calculate moment, yeah? And of course, we're going to break it down into, right now we are in a 3D environment, which is you have your X and the Y and then your Z axis, and of course your point of interest right there, and then you have your force, and then you have your location, yeah, which is position. And we're going to break it down into three components because we have three axes. And we do the same thing, Fx, Z, and then Y. And then we have Rx, and then Ry, and then Rz, okay? Of course, your final moment about the origin is going to be the R times F, okay? In physics, you go straight to that, but if you want more precision or accuracy, of course, it's better to break it down into different components, yeah? And get the mean of it. And we will go into 6.3-1. So here's your very first thing to be able to know how to operate the cross product method. We have to do the cross product method because you're dealing with the 3D, which is a three-dimensional environment, and we're breaking down the components into three axes. Yeah. So therefore, you have I, J, and I, J, and K. Yeah. Unit vector. We make it unit vector to get our direction and the value, of course. And your questions asking you to calculate the moment created by force F about the origin O using the cross product if the location of the force's point of application is given by R. Yeah. So now we have our force and location. You only, every time you think about moment, you look for the force and then you look for the multiplier, which is your distance. Yeah. We can make this force bigger and you get that because you're multiplying with this distance, okay? And so what you're gonna do is now you have issue. So your issue is not easy like in physics anymore. There is factors in it. So you're like, oh, I don't know how to do it. So we are going to make it really easy by using matrix, into the cross product method. Of course, in our cross product method, we are going to put our unit vectors. So we're dealing with the 3D, so therefore I, J, and then K. This is just showing you that we're dealing with the vectors. And then we're going to put in a matrix like this, and then we're going to put a corresponding value in it. So I've got 2 here, and I've got another 2 here, so I'm just going to write it down in a column. And then your J, yes, and And then of course, sorry, I need to drink some water because my voice is disappearing. Okay, I'm back. It's not getting better, but whatever. So anyway, so being a professor is no good because we gotta talk a lot. Yes. Okay, so then of course you another thing that I know that students always have confusion. Their confusion is do I write this thing first and do I write that thing first, right? Let's just go with the order. So since you have like R times F, yeah, we are going to write the R first. Okay, so you have 2, 3, so therefore 2 and then 3, because you always have a confusion. I have like a 2 here, but then what am I going to put here? Do I put like a minus 0.5 here and 3 here? You know, so you guys do that all the time. So don't do that. Or you have to just go in order, because the order of your equation set, please start with R position. So therefore you're going to put the position there. And then your force minus 0.5 here. And you don't have K, but you are in 3D, yeah, because it said so here. So therefore you go back and then you're going to add the last unit factor, which is K. Okay, I'm back. Oh my gosh. So anyway, so no, a little bit better. So anyway, so let's go back to here. So we know how to position all of this in the matrix. Yeah, so start with the R, followed by your F, and then we are going to put the last axis, which because you have the third axis, so you need the last unit vector, which is your K. Okay, and then put that in, and we are going to do the cross product. Okay. Of course, you're going to tell me, oh, how do I get from here to here? So I wrote everything here for you, okay? So we go on to example 6.3-1, and I upload this file in your question answer module up in your Brightspace, and you are going to see it, okay? And so here we go. We're going back to here. So we're here, yeah? So what we do is the very first thing that you have to do is to do the cross product method, okay? So let me get a drawing thing here. So the cross product method is the first thing that you gotta know is which one that you are, okay, starting. So you're gonna start it always in the order, which is I, J, and K. Yeah, so that's the first thing that we do. See, we put it in the order I, J, and then K. So your I, okay, if you want to calculate I, okay, and what's its coefficient is going to be, okay? So in cross product, if you want to calculate I, ignore that column. We will use only the second and the third column in the matrix, okay? So you're going to multiply this, okay, with that. And then you are going to multiply this with this. See how the cross is. And that's what exactly we did it, yeah? 3 times 0. And then 0 times minus 0.5. See? I mean, cross method operation is like that. Of course, you subtract it. Okay? So that's what you have to do. Cross method. Yeah, so if you calculate it, you get 0. That's how we get the 0. Then the next one. So let me get my eraser. Where's my eraser? Then we will go to, yes, J. So if you want J, we do the same thing. Yes, since we want J, we are going to use I and K. Yeah, so we will use I and K. So you will multiply 2 with 0, see? And then 2 with 0, okay? So that's what we do. So you get 0. The last one, we are going to get K. So if you want to get K, yeah, we will use this. So you go 2 times minus 0.5 and then 2 times 3, and this is what we did. Of course, don't forget to subtract This is subtraction right here. I point it out for you so you don't forget it. All right. And of course, and you need to know the sign of I. Okay, the sign of I is positive. Okay. And the sign of J is negative. Yeah, because you multiply this and this. And sign of K is positive. Okay. And if you cannot see that, okay, I will show you directly because sometimes you have issue seeing it. Okay. So let me erase this. All of this. This is just confusing. Of course, this is positive and positive, so you get positive. Positive and negative, you get negative here. Positive and positive, you get positive here. Okay? So now we don't have that. So all you have is a -7 K. Yes, the result. Now we come back to here. So now you know how we get this. Okay? Alright. The next one is 6.3-2. Let me see if we cover. Yeah, we cover this one. So anyway, so it's just giving you some boxes here, and then it just asks you, okay, which one is going to tip over. So all you have to just draw, straight lined like that. So that's where your gravity, yes, is pulling you down that way. So when you look at it, this guy, is off of the support. Your support is from here to here. So this B and C is in the support, and A and D is out of the support. So therefore they will definitely tip. So this guy and that guy will tip over. This one won't tip over because it is the force that is being subjected to this guy pulling down is right on the slope underneath of this object. Okay, meaning like the force is against this triangular structure. Yeah. You now here see like how this force has an empty space here between this object and that structure. Yeah. So therefore, this force can pull it down. Yeah. So it will tip over. So that's what you're seeing. Okay. So let's go. Yeah, I'm right. Okay, so you go down, so E and D, okay, is going to tip over. This one will not, because this is, I think, a bigger, support, and this is a smaller support. I also did that for you, okay, in this handout. That's from your digital textbook. Just showing you, yeah. And of course, I explained that here, a box will tip over if the vertical line, passing through its center of gravity, this guy MG point, is going to fall outside the base of support. Typically the bottom corner or edge touching the inclined surface in this example, of course. Then of course we will go back to the slide. We have another one. Okay, another example is asking you to, okay, you need to loosen a very tight nut. So anyway, so this is a nut, you're going to loosen that tight nut. So which arrangement would be the most effective? Rank them from best to worst. So you have a nut, and then you have a force, yes? Then the force in the center of that nut has a distance, okay? So you gotta pay attention to that distance. So you just draw a line like that, okay? And compare them, of course. So you can clearly see this thing is so, right, long. So therefore, the question asking you which one is effective, the most effective system is with the greatest force. So the only thing that is going to give you the biggest force is with the longest, right, R. So this guy, and of course this is also completely 90 degrees, so it's even better, yeah. So if you have like an angle like that, it's not very good, it's weak. If you have like a 90-degree force, it's very, very strong force, and you will be very effective in loosening that nut, okay. So here, loosening that nut, here they're about the same, yeah, about the same distance, but they're slightly different because of the R, yeah. When you look at it, they're about the same. And this is the worst position, is because the rest of them are at 90 degree, yeah, and they have like the same distance, so therefore these are more effective than that guy, yeah. The D is the least effective, the worst. And A and C, when you look at, they are the same, yeah. The only thing that is different is the structure. This structure has like a external component, which is this guy, but this has no effect on that force, because the force that's been created here is called moment, and that moment depends only on the distance and the force. It has nothing to do with whatever structure on that line of force, okay. So therefore this and this is completely equal to each other. So you rank it like that, okay. D is bad, this is good, and this is okay. They give you some, okay. So that's all correct. Of course, I also put it here for you. I wrote it differently, okay. So the answer, I wrote it differently. I wrote it here like your maximum torque, because we usually call it torque every time you have to deal with the distance and some force to create another force here. So your maximum torque is B, the worst torque is D, and then your A and C, they have equal torque, which is less than B but greater than D, okay. Alright, so what I'm going to do is let me see, I will stop at the moment and then record the other one, okay, the last section 4, I think, section 5 actually, yeah, this is 1 to 4, and then I'm going to record the section 5 in a different video. Okay, so why calculating moment is important? It's very important because you are creating force, by using applied force with some distance. So that's a pretty useful technique to create force. And we've been doing that, since long time ago. Like Egyptians are building the pyramids and stuff like that. They use nothing but that apply force people, and then some wood or something like giant wood to create that position, okay, or distance, to create bigger force. So it helps determine how forces cause objects to rotate. Okay, and this is what we're doing. So translation is inducing the rotational force, ensuring the structure stability and the mechanical balance. Yeah, that just being formal. And what you want to say is that moment is very, very important because it creates rotational force by using translational force. Okay. Here, real world example. We create the force, and here is your own thing, and then of course we can be able to lift this car up with this crane. Yes, you are creating the moment right here, rotational force. You're gonna pull it up. See, now look at that. It's the rescue mission has failed because of this. Okay, torque imbalances that situation. Yeah, it didn't do it in the way it wanted to be, because look at this, it's not, not a very good designed whatever they're using right here. So it went down with the gravity. Oh my gosh. So now you gotta come with a different okay with a different arm here to pull this again. Here is your moment. So the first example, the moment mess up. The second example, yeah, pulling this up, and you get this car up, yeah, and now it is going to take the other one. Look at this, yeah. So this distance, okay, is adjustable, yeah, and see how it extended. Look at this. I'm gonna go back and show you. See, like this gap where it can be extended. See, it's a extended R here, making R longer. Yes, so therefore you can be able to create a greater moment or greater rotational force here, which is gonna pull this truck up. Okay, so therefore the moments are very, very important. Oh, look at this, it's go down again. So it means like this guy, right, has a more force, yeah, so this is not enough. You have to use a different stronger force, yeah, because this force is not enough, because this guy has a more gravitational forces, because of the mass, yeah, is very big. So I am gonna stop the first lecture video right here for you to use, and I will go into the mass moment of inertia. Let me see if we are covering it this semester. Yes, so we are covering it this semester. So therefore, I'm going to go into that in next video.